All right, welcome everyone. In today's lecture, we are going to bridge the gap between, well, the abstract world of equations that you see in textbooks and the very real, concrete world of business operations. We're going to move beyond the theory and really demonstrate how mathematics isn't just a class you have to take, but an absolutely essential tool for management, for strategic planning, and of course, for profitability. So, I want you to keep this one question in your mind as we go through the material today. Seriously, how does math really run a factory? When you picture a busy factory floor, with all the machines humming, materials moving around, people working, you probably don't immediately think of linear algebra. But I promise you, underneath all that organized chaos is a very precise mathematical framework. And that framework dictates every single strategic decision, from what to build to how to use your resources. Our job today is to take that framework apart and see how it works. At its core, every single business, I don't care if it's a giant multinational corporation or a small local shop, faces the exact same fundamental challenge. It's like a puzzle. You're constantly juggling what you want to produce with the resources you actually have. This is the central problem of what we call operations management. Now, in business, we call these limitations constraints. A constraint is really just anything that limits you from reaching your goals. In a factory, that could be the 40 hours in a work week, right? Or the limited amount of steel you have in your warehouse, or even the maximum speed of a specific machine. The sign of a truly great manager isn't having unlimited resources. Nobody has that. It's about being brilliant at optimizing the limited resources they do have. And it's right at that point, right there, where a systematic mathematical approach becomes not just helpful, but absolutely necessary. Okay, so to tackle this puzzle systematically, we need a tool. And that tool comes from algebra, the system of linear equations. Now, here's the formal textbook definition. It's a collection of two or more linear equations that all use the same set of variables. But let's immediately translate that academic speak into something that actually makes sense for business. Think of it this way. Each one of those constraints we just talked about, the limited labor hours, the finite materials, each one becomes a rule. And each rule becomes an equation in our system. So each equation sets a boundary line that our production plan just can't cross. A system of equations, then, is really just the complete rulebook for our factory's operations, written out in the clear, precise language of math. So if a system of equations is the rulebook, then a matrix is the executive summary. As business problems get more complex, and trust me, they do, with dozens of products and resources, writing out long lists of equations just becomes clunky and inefficient. Matrices give us this incredibly powerful, super compact way to represent and work with the entire rulebook all at once. So I don't want you to see it as a complication, it's a tool for clarity. Let's ground this in a concrete example. Imagine our factory makes two things, product A, which we'll call X, and product B, which we'll call Y. Now, our production is limited by two main resources. The first equation, 3x plus 2y equals 100, is about resource R1. Let's say R1 is labor hours. So this equation is telling us that to make 1 unit of product A, it takes 3 hours of labor. And to make 1 unit of product B, it takes 2 hours. For this production run, we have exactly 100 labor hours available. The second equation, 2x plus 4y equals 80, works the same way for resource R2. Maybe R2 is, say, kilograms of steel. I find this is the best way to think about it. The matrix is like the main control panel for your entire business operation. And we're about to build this panel where every single number has a specific place and a very precise job. A good manager can just glance at this panel and understand the whole production system. Building the matrix itself is actually a very logical, straightforward process. First, we just confirm our variables. X for product A, Y for product B. Easy enough. Second, we look at our equations, and we just pull out the coefficients. Those are the numbers attached to our variables. So from that first equation, we grab the 3 and the 2. From the second, we grab the 2 and the 4. And third, we just arrange these numbers into a little grid or an array, making sure we keep them in their original spot. And here you see the result of that process. It's actually quite elegant, isn't it? We've created a matrix equation. On the left, that first box with the numbers 3, 2, and 2, 4, that's our coefficient matrix. That is the heart of our production model. It's multiplied by the variable vector, which represents our products, and it's all set equal to the constant vector on the right, which represents our available resources. All of that information from those two sentences of equations is now captured right here, in this one compact statement. Okay, so we've built the model. Now we have to shift gears. We have to stop thinking like mathematicians for a second and start thinking like managers. It's not enough to just build the tool. We have to know how to read it, how to interpret it, and how to use it to make smart, data-driven decisions. This is where the theory becomes practice. I want you to really put yourself in this role. You're the manager, you're standing on the factory floor, and you're looking at this matrix. What does that number 4 on the bottom right actually mean? Is it 4 boxes of screws? Is it 4 hours of machine time? This is the key. Connecting these abstract numbers to tangible, physical things in your factory is the secret to mastering business mathematics. So let's dissect this matrix, because this is so important. Look at row 1, the numbers 3, 2. This tells a story about resource R1, our labor hours. It's the recipe for how we use labor. For every unit of product A we make, we use 3 hours. For every unit of product B, we use 2. But if we read the matrix vertically, down column 1, the numbers 3, 2 tell a completely different story. This is the complete bill of materials for making 1 unit of product A. To make just 1A, you need 3 units of R1 and 2 units of R2. So you see, reading across the rows tells you about your resources. Reading down the columns tells you about your products. And that vector on the right, 180, well, that's just your inventory list. It's what you have on hand in the warehouse. Okay, this brings us to an absolutely crucial point. And please, everyone, really focus on this because it is one of the most common and damaging mistakes that students make. You cannot mix up your rows and your columns. If you build this matrix incorrectly, every single calculation you do from that point on will be completely wrong and operationally useless. So here's the easy way to remember it. Rows represent resources. Both start with R. Columns correspond to your products. Rows are resources, columns are products. If you can just burn that into your brain, you are well on your way. So up to this point, our entire focus has been on what's possible, right? What can we produce, given the stuff we have? But a successful company isn't just about being busy, it's about being profitable. So now we have to connect our operational model to the financial engine of the company, the bottom line. When we solve our matrix equation, and we'll get into the methods for doing that in a later lecture, it's going to give us a specific number for X and a specific number for Y. That solution tells us the exact number of product A and product B we should make to use up our resources perfectly. And that is a critical piece of information, but it's not the end of the story. The ultimate reason we do all of this work is to use that production data to drive a financial strategy that gives us the biggest profit possible. Now to do that, we bring in 3 new functions. First, there's the cost function, C of XY. In our little example, let's say it costs us $5 for every unit of product A we make, and $10 for every unit of product B. So our total cost is 5X plus 10Y. Second, the revenue function, R of XY. We sell product A for $20 and product B for $15, so our total revenue is 20X plus 15Y. And finally, the most important one, the profit function, P of XY, which is, as you know, simply revenue minus cost. The key thing to see here is that our operational decisions, the values of X and Y, are what drive all 3 of these financial outcomes. And here is the grand synthesis. This is where operations and finance come together. The entire reason we go through the hard work of setting up and solving that system of equations is to find the one unique combination of X and Y that is feasible, meaning it follows all our rules, and at the same time makes that profit function as big as it can possibly be. We're looking for the optimal production mix. This isn't about guesswork or a manager's gut feeling. It's a precise, data-driven method for making the best possible business decision. So let's just do a quick recap of the key takeaways from today. First, we've seen that linear equations are how we define the rules of the game in our business. Second, we've learned that matrices aren't just some abstract math concept, they're powerful dashboards that organize all this complex data. Third, by solving these systems, we find the absolute best way to use our limited resources. And most importantly, we've connected this entire operational framework directly to the ultimate business goal, maximizing profit. I really want you to carry this idea with you as you continue your studies. The quantitative skills you are building in this course aren't just academic hurdles to jump over. They are powerful, practical tools that you will actually use to analyze complex problems, to create strategies, and to make smart, defensible, data-driven decisions throughout your entire career. Before we wrap up, I'm going to leave you with a little thought exercise for our next session. Let's throw in a real-world problem. Imagine the price of a key raw material for product B suddenly doubles overnight. How does that event change the mathematical model we built today? Specifically, which part of our model gets adjusted? Would you change the constraint matrix, the one that governs what's possible to produce? Or would you change the coefficients in the cost function, which determines your profit? And here's the big question. How would that one single change ripple through the entire system to give you a brand new, different optimal production plan? Think about that, because adapting to those kinds of dynamic changes, well, that's what modern management is all about. Thank you for your attention.